Hello everyone, in today's video we will do a mole balance of a plug flow reactor, which is PFR. PFRs are tubular reactors where the concentration changes horizontally and does not change vertically. We also need to consider that we'll be using a small section of the reactor as our volume. We'll call it dV. So the small section will be performing a mole balance in that small section, which is we'll be considering the moles flowing in, the moles flowing out. So let's go ahead and start with our mole balance, which is moles entering minus moles leaving plus generation, which is RA times dV for our volume, which is this here, that small slice, equals accumulation, which we're assuming also the plug flow reactor to be in steady state, therefore the accumulation will be 0. Let's go ahead and solve for the volume, differential volume. dV equals final amount of moles minus the initial amount of moles over the rate of reaction. Okay. Final moles leaving minus the initial moles, that can also be written as the change in FA, and it can also be written as dFA. So therefore dV equals change in moles over rate of reaction. Okay, now using the conversion law, which states that X stands for conversion, equals the mole of A reacted over total moles of A, which equals to FA naught, which is the initial amount of moles or the total amount of moles, minus how many moles are leaving the system, over FA naught, which is the total amount of moles. Solving for FA, which you'll end up something like this, we'll cross multiply. FA naught X equals FA naught minus FA. Therefore FA equals FA naught times X. FA naught minus FA naught X, leaving us with FA equals FA naught times 1 minus X. Okay, so what we're doing right now is this equation here, we're writing it in terms of X, which is the distance of the plug flow rate reactor. So we're changing it in terms of change in moles. We're changing it to change in distance. The X is the distance horizontally throughout the reactor. We'll notice later on that as the X value increases, as we go down the value of conversion increases, and the concentration of A that's being the reactant of A is being consumed, and B is increasing, which is what's being produced. Anyway, we can go ahead and sub in this term over there, but we're looking for dFA. We have so far FA, so we'll find the dFA, the differential of FA in terms of dx. Therefore, you'll be negative fa 0, fa naught, which we're basically getting the derivative of this, which is dfa over dfx equals 0 minus fa naught, which equals to fa naught. Okay, so dfa equals negative fa naught dx. We can go ahead and sub this term right over there. Okay, so I'll go ahead and write it again. dv equals dfa over rate of reaction. dv will equal to negative fa naught dx over the rate of reaction. Okay, now the rate of reaction, as we said in the previous videos, it could be first order, and the reason behind this negative here is because A is a reactant which is being consumed, therefore it's minus. It could also be in second order, and it can be a mix of reactants. Okay, for the sake of this video, we'll go with the simplest option, which is a first order rate of reaction, and we'll go ahead and sub it into our equation. Therefore, dv equals negative fa naught dx over negative k ca. Now, the same rule applies to the concentration of A as Fa here. So Fa, we said, equals to Fa naught, the initial amount of moles, times 1 minus x. Okay. The same law applies. So the final concentration equals the initial concentration times 1 minus x, which is the conversion. You can go ahead and sub that here, just because we don't have the final concentration to work with, and the initial concentration is given, so it can be used as a constant. Also, we're trying to convert as much variables as we can in terms of x, in terms of conversion. Therefore, dv equals negative fa naught over negative k ca naught, the initial concentration, times 1 minus x. You can go ahead and cancel these negatives. dx. Okay. Now we know that concentration equals to the mole flow rate over the volumetric flow rate. Therefore, the volumetric flow rate, which is small v here, because I don't want to get it mixed up with the volume, the small v, which is the volumetric flow rate, equals the molar flow rate over the concentration. We can see here that Fa naught over Ca naught will give you the molar flow rate. Therefore, dV equals molar flow rate over K. Okay, we'll integral both sides. 1 over 1 minus x dx from 0 to v, from 0 to x. Therefore, the volume equals to volumetric flow rate over K, the integral of 1 over 1 minus x dx, which equals to volumetric flow rate over K, negative ln 1 minus x, which is V equals negative V, negative volumetric flow rate over K, ln 1 minus x. And that's the volume of the plug flow reactor that we'll be working with. That's the formula you'll use to size your plug flow reactor, and it depends again on the rate of reaction. It could be first order, second, or mixed. It also depends on if the reactor is isothermal or not. If it's isothermal, then K will be a constant. If not, then K will be a function of temperature. We'll do another example on a plug flow rate reactor. Thank you and bye bye.